Hello everyone, welcome to Pepcoding. So in this video, we are going to start a new question of our tree series. Okay. So the question that we have this time is in order Morris traversal in binary tree. Okay. So we already know about in order traversal, right? But what is this Morris traversal? So let us see what is this, and after that we will discuss that how to do this question. Okay. So what is in order traversal? First of all, let us see that, as we all know, okay, in order traversal is we did this with the help of recursion. So what we did is we called first one left call, okay, left call first, then some work like printing between left and right call. Okay, it is my right call. So we have two calls, first is left, and second one is right. So in between that, the work that we are doing is in order work, right? And in this work, if we are printing the nodes data, okay, if we are printing the data of our nodes, then that will be called as the in order printing. Okay, so suppose how I'll start is, what I'll do, I'll start from here. Okay, this is the left call has started from here, so it will go to the left of the tree first. Okay, so left will come here. Okay, first of all I'll come here, then I'll go to this node. Okay, and after this it will make its left call, and it will say that the left is null. Okay, and after this it will come here because it will return from here when the null will encounter, when it will encounter a null pointer, then what it will do, it will print this. So 2 will be printed first. Okay, so 2 is printed, and then uh the right call will also say that it is null here. Okay, so now it will go to 7, it will go to 7. So when it will go to 7, then the left call is already been completed for 7, right? Then after this, now the 7 will be printed, and the right call of 7 will take place. So here the call for the right call for 7 will take it here. Okay, I'm at 6 now. So after 6, what I will do, I'll first make my left call. So left call here. Okay, 7 is already printed, left call here, and then we will reach to 5. Okay, and after making the right call and the left call of after making the left call of 5 will print itself and will make its right call. Okay, and after making its right call, it will go to 6, it will go to 6 again. And as we already know that the left call is done for 6, so 6 will also print itself, and then it will make its right call. So right call will take it here in at 11. So after coming to 11, what it will do, it will make its left call first. Okay, print 11, make the 11 right call of 11, and after making the 11 right call, it will go to this 2, right? This 2, so it will come here. So after coming here, the left call for 2 is already been completed, so 2 will print itself first and will go to the right now. Okay, print and will go to the right now. So after coming to the right, it will first make its left call. Okay, the right call will take it here again. Okay, back to the, suppose it is my function in order is the name. So it will, what it will do again, take it to the left call. Okay, and when it will make the left call, then it will return from there, right? Because it is left is null. So it will come back here again and will print first of 5 will be printed first, and after that the right call will take place. So right call will take it here. Okay, now after this, what it will do, it will take it to the left. So it will come here, right? It will come here, and after making its left call, it will again print 4. Okay, and then after printing 4, what it will do, it will make its right call and will take it to here at 9. So left call is already done for 9, so 9 will also print itself, make its right call again. Okay, from there it will return, and then this is how it will be completed. Okay, so this is my in order traversal. This should be printed when I will complete this question. Okay, this should be printed. So but in this question, what I will do is, I'll not take the help of recursion or any extra space. Okay, I'm not going to take the help of recursion, because this time I'm coming back to this 7 with the help of recursion, because it is returning from here. The left call is being exhausted, right? The left call is being completed. Now for the right call, it will come back to 7, and then it will make its right call here, right? For this node, I'm saying that I'm going to 2 first. Okay, and when I'm saying that I don't have any call in the left round, okay, I don't have any call in the left side, so I'll return to 7. And after returning to 7, what I'll do is I'll go to my right, because I have one more right call left after printing. Okay, printing, and then I have one more right call left, so I'll make the right call now. So this is how I'm traversing in this in pre-order. But I cannot do this in this question, because in this question we are going to learn a new technique that is Morris traversal. Okay, that is Morris traversal. So what is this Morris traversal and how is it useful and why we are using this, as we have already learned the in-order traversal by recursion. So why we are using this, why is it important? So with the help of Morris traversal, what we can do is we can print the in order. Okay, in this question we are going to print the in order. In next question we are also be printing pre-order. Okay, so we can print in order with, we can say without any extra space or without any recursion. Okay, without recursion or without extra space, we can traverse into this tree. Okay, and it is so cool that we are not using any extra space, right? Because in recursion also we are using extra space of stack, right? Let us make the stack first of all. Okay, let me show you that how the stack is filling in pre-order for in recursion. Okay, in order of recursion. Okay, so let us see. So first of all, here what I will do is 2. First of all, I will be at 2, right? So this is my recursion stack. So what I'll do is, first of all, it will make the call for 2 left, right? 2 left call will take place first, and then it will go to 7, then 7 left. Okay, and then 2 left. So left, then print, and then right. This is the order, right? Print, right, and these are calls. So these are calls. So what I'll do is 2 will be printed now. Okay, because the left call is being completed for 2, so 2 will be printed first. So 2 will be printed, and after that it will say that make my right call. So 2 right. So after making 2 left and 2 right call, okay, the right call of 2 and the left call of 2, it will say that all the calls are completed for 2. You can come out of this stack. So now it will go to this position. So now we are at this, right? 7 left call is done, so we will print 7 first, and then we'll make 7 right call. Okay, we'll make the right call of 7. So right call will take it to 6, right? So now what will happen is 6 will say that make my left call. Okay, so make my left call. So left call will take it to 5. So 5 will say make my left call, 5 will say print me, and 5 will say make my right call. Okay, so this is what we will do for 5. Okay, and as the both calls are completed for 5, so 5 will come out of this stack. Okay, or we can say that 5 will be raised from the stack. So yeah, so now 5 is printed. Now we'll reach to 6. Okay, the left call is done for 6, so 6 will also be printed now, and the 6 right call will be made. Okay, 6 right call will be made, and we will reach at 11. Similarly, 11 left and 11 right, 11 left, and then printing 11 and 11 right call will made. Okay, these two call like first left call, then printed, and then right call. Okay, this will be done, and then 11 will also be erased. 11 will also be erased. Now what is happening is, see, it is done for 11, right? So now it will go to 6. So when it will go to 6, 6 will say my both call are completed. Now what I can do? So simply you can come out of the stack. Okay, so now it will say I'll go back to 7. So 7 will say, okay, I'm also done with both my calls. So what I can do now? Nothing. You cannot do anything, as you are done with both of your calls. So it is also erased. Okay, it will also be erased. So this is how my stack will look like now. Okay, so I'll come to this position, and then I'll go to right, because it will say that I have a right call left. So 2 right. Okay, now 5 will make it left call, but it won't get anything, because it does not have anything in the. Okay, first of all, after this it will print 2. Okay, print 2, and then we'll make 2 right, and then 5 will make its left call, will not get anything, and then print 5. Okay, it will print 5 and will come to 5 right call. After printing 5 right call, and then it will say, it will come to 9 left. Okay, 9 will make it left call. So after making its left call, it will say 4 left. Okay, 4 left, and then after 4 left, this will be the 4 left, right? So after 4 left, 4 will be printed, and then 4 right call will be made. So when we'll make the 4 right call, okay, the right call of 4, then after that it will say that I'm done with both my calls. So it will say come out of the stack. So now what it will do is it will print 9 as it will reach to 9 this time, right? Because left call is done for 9, printing will be done, so 9 will be printed. Okay, and after that 9 right call will be made, and it is null, so both the calls are completed. So it will also come out of the stack, then it will go to this, right? Then it will go to 5. So after coming to 5, what it will do, it will go to this 5 is also done with both of this call, and it will also come, and 2 is also done. Okay, so this is how the stack trace will look like at the time of pre-order. Okay, we can see that we are using stack continuously. Okay, we are first making 2 left call, okay, left call of 2, then left call of 7, then left call of 2 again. Okay, so this is how we are filling the stack. But in Morrison traversal, we are not going to use any recursion, so we are not taking any stack space. Okay, any space of stack, we are not going to use it. Okay, again, second thing, we are not going to take help of recursion. Okay, so no stack will be needed now. Okay, and nothing, no else data structure will be needed. Okay, not even array. Okay, and but that is different, that if we need to return the answer in the form of some array list or some vector, okay, so that is a different thing. But in this, we are not going to use any extra space. So this is why this is so much important. Okay, this is why the Morrison traversal is so much important. So how we can do this Morrison traversal? Okay, we have already discussed about this Morrison traversal. Okay, why is it important? We have already discussed it, and the concept behind this is, we can say, threaded binary tree. Okay, threaded binary tree. So what is it? So let me give you a little gist of this Morris traversal, right? Let me give you a little gist of this. So what will happen in this is, in this case, what we will do, see, we are not going to use any recursion here, right? So I'll be traveling from here, I'll go here, then I'll come to this, but when I'll come to this, I cannot now go back to my children. I mean, I'm my parent. I cannot go back to my parent because the link is from parent to children, not from children to parent, right? So how I can go back? So this is what I need to understand first of all, because if I need to traverse in order, so in order cannot be changed, because in order for a tree will be always look like 5, then 6, then 11, then 2, then again 5, 4, 9 will always look like this. Okay, the tree, the in order will also always be same. Okay, this will not be changed, and but what will be changed? The techniques for printing this, the techniques for printing this will be changed. So now the technique we are using is Morris traversal. Okay, so the technique which we are using is Morris traversal. So how we can do that is, see, so already told you about this problem that we are facing, that if we are not using recursion, then I cannot go back. Okay, so how we can do this? We need to find a solution. So see, if I have a link from this to this, so can I go to this? Yes. Suppose if in the right of this 2, I'll attach this 7 somehow. Okay, I'll attach this 7, so I can easily reach from here to here, right? So this is the first thing what I need to do. I need to make some connections. So similarly, when I'll go here, so I can come here as I have link, but when I'll come here, I cannot come back to this, so I'll make again a connection here. Okay, and now From here I can come here, right? And from here I again have to make a connection so that I can go to this two. Okay, now from here no needed. Okay, it is not needed. Like I'll reach here, then I need to go there, right? And then I need to go here. From this to this I can go easily, right? But from here to here again I need a connection. Again I need a connection. So this is how I can traverse a tree. How I can traverse a tree? See, we have connections, right? uh, we have these connections from 2 to 7, from 7 to 2, right? So I can travel from 2 to 7 to 2, right? 2 7 2 I can travel, but I need to go from here to here. So for that I need to make connection. So suppose I made a connection from here to here, I can come, from here to here I can come, from here to here I need to make a connection. Similarly, from this to this I need to make a connection, and from this to this also I need to make a connection. So if I traverse this now, see, can I traverse this tree now? Okay, I can traverse this tree now. So this is how it was just a gist that we are going to use in this question. Okay, it was just a gist of this. So but if we'll keep this connection as it is, right? If we'll keep this connection as it is, like I'll join this 2 to 7, so my tree will be changed, but I cannot change the data that I have, right? So I need to think about that also. So this connection that I'm making right now are threads, are called threads. So this is what the threaded binary tree is. Okay, this is the concept of threaded binary tree, that I'll make some threads to join my nodes so that I can traverse into this tree. Okay, so this is the concept of threaded binary tree which we are going to use here. So I hope that you understand this threaded binary tree, and let us see that how we can do this Morris traversal. Okay, how we can do this Morris traversal. So first of all we will understand that how we can do this. Okay, and then we will see the code. Okay, and then we will see the code, and in code we will again see that what we have discussed here. Okay, we will see that what we have discussed here, we will write only that. Okay, we'll write only what I have told you in this dry run. Okay, we'll write the same thing in our code. Okay, because what happens is, when we understand a code and we understand the dry run, then it is quite easy to convert it into the code. Okay, it is quite easy to convert it into the code if we understand the dry run properly. So we will focus on dry run first. Okay, so let us start. So I'm discussing how here. Okay, I'm discussing how we can do this. So what I'll do is, I'll put a pointer here. I'll put my current pointer here. Okay, so what are the conditions when I print in my inorder? What are the conditions? See, I traverse this way, from this to this to this, and when this side ends, when this left side ends, this is the first member which will be printed. So first of all we need to understand that when the left side will be ended, when there is no node in the left side, no node in left, then at that time this member will be the person which will be included in my inorder, right? So it is done, right? It is done. We understand this. And now this thing, if we have traversed this side, we completely traverse this side, this subtree, then at that time we are going to add this into our inorder, right? Suppose if we have processed this subtree, we have completed this subtree, then we will add this two, right? So there are two conditions: if there is no node in the left, okay, and second is if we have processed the left subtree, then in these two conditions we are going to add or print our node data. Okay, so these are the two conditions. And otherwise we always go to the left side only, right? We never go to right. We only go to right in the two conditions, that is, when the left call are exhausted, we go to right? When left calls are exhausted, we go to right. And then the second thing is, we go to right when the left subtree is processed. Go to right. Okay, left calls are exhausted, go to right. Left subtree is processed, go to right. So these are the two conditions. Okay, So this is what I need to do. So what I'll do is I'll keep my pointer current here, okay, and I'll make a left node, okay. I'll make a left node to the left of this current, okay. And then what I will do is, I already have told you that for traversing this I need some threads, so I need to make some connections. So how I will do this is, see, I'll place a current in the root first, okay, and then will place a left node to its left, okay. And what I'll say this to this left node is, I'll say give me the rightmost node of this left node. So what it will do, it will give me the rightmost node, that is this, okay. ln will come to this, okay. I'll write this cross to mark how many times it is visited, okay. It is visited first time, it is also visited first time, then one this and one this. So when I came here, okay, when I came to the rightmost, I need rightmost node, okay. When I have this rightmost node, let me write the steps properly. So I need this rightmost node, okay. So after this rightmost node, what I'll do is I'll check if the right of this rightmost node is null or not, okay. If it is null, then that means that there is no connections, that means there is no connection, right? If the rightmost is null, that means there is no connection to this. So at that time I'll make a connection, okay. At that time I'll make a connection. We are understanding just how only right now, okay, and why we will discuss this later, okay. Why we'll discuss later. So let us concentrate on how first, okay. So how it will be done, we'll take a pointer at the root and then we'll place a left node to it. We'll take out the rightmost node and we'll make a connection to its current, right? So after making the connection, what I'll do is I'll shift my pointers, that is this left node and this current, okay, to the left. Only current will be shifted, right? Because see, after shifting this, I make my left node to the left of it, okay. Now I'll create my left node, okay. I'm not shifting both of them, I'm just shifting one, and what I'm doing, I'm making one left node to the left of it, okay. So that is what it is. So here we can see the left node is not null, right? At this point, when the left node is not null, see, I'm writing here, when left node is not null, not equal to null. So at that point, what we did, we need rightmost, and we checked if null or not, okay. So this is what we do, we placed a left node, okay. We placed a left node, and after that left node we checked if it is null or not, because see, you will say that where you have checked that if it is null or not. See, I'll do see, in this case, here I have C, here I have left node, so the rightmost node is this only, right? I need the rightmost node of this left node, so the rightmost node for this left node will be this only, right? So I'll make a connection again. If there is no connection to the rightmost of right, I'll check if the rightmost of right is equals to null or not, okay. Rightmost, I'll take out the rightmost and I'll check if rightmost, right of rightmost, where I can write it, rightmost right, okay. I'll write it here, okay. If the rightmost right, see, the right of rightmost is null here, right? The right pointer of right, it was the rightmost, and the right pointer of it was null. So when it was null, I make a connection. So here it was also null, I made a connection, and after making the connection, shifted, okay, shifted. So it was visited first at this time, and now second, the C is coming here, okay. C is coming here, and again it is also visited 2 times. because first because of ln, and then c will come, c also came here, so it is visited 2 times. Now when we will create our left node, so left node will be created in the null, right? Because left node is created to the left of current. Left of current is left node, right? Left node is left of current. Left node is left of current. So now it is null. So when it is null, I can see that this time my left side is already being completed, right? Left side is already being completed. So at this point, I'll add my current data. I'll add my data of this current pointer. So the data is at this is 2, right? I don't have anything in the left. So what I'll do, I'll add this to my this, I'll print it, okay, or I'll add this to anything like any vector or array list or any array in which I want, okay. I'll add it, and then after this what I'll do, after adding this, I'll make the call for the write, right? So now I'll say that I have established the connection before, okay. I established the connection, that is, I established the connection from the right of this to current to this, right? So what I'll do is I'll take this current to the right of it. So after this will be moved here, this will be moved here, okay. So if you are not understanding this right now, okay, so do not worry, because we will do more iterations, and after 1 or 2 or 3 iterations you will understand it, okay. So here it is visited the third time, okay, it is visited third time. So again the same thing, make left node, take out the rightmost node. So this time rightmost node is 2, right? It is also visited third time. So rightmost node is 2 this time. So when rightmost node is 2, we'll check the right of rightmost. So right of rightmost is current again. So this time what I'm saying is, I'm saying that right of rightmost is not null, right? Right of rightmost is not null. What that means? That means that my child can access me. My child can access its parent. Right? Here we have the access of its parent, but it doesn't happen in tree. The child does not have the access to its parent. So what will happen? What is happened here? So at this point, I can see that I already have visited that side. I already have completed and processed that side. So I will add it to my tree. I will add it to my in order. Okay, that means 7 will be added. It is too much of hodgepodge. So I'll not write this here. I'll write this. I'll write this here. Okay, so what we had 2, and now we see the left side is processed, so we will make 7 again. Okay, we will again add 7 into it. And one more thing, c is here, ln is here, right? So what we will do right now is, now we know that the rightmost is not null, okay, and it is equals to some connection that is going to our current node, right? So we will add 7 into it, and we will also destroy this connection, because we don't want to change our tree, okay. And we will take this current to this end, to its right. We will take the current to its right now. So what we did, we visited from this to this to this, okay. We again went to this, and now we went to this. Are you seeing this? It is completely same as that of our Euler path, right? It is completely same as that of our Euler path. So this is how we are going to process in it, okay. This is how we are going to process in it. So let us do the same thing again, okay. Let us do the same thing again. So we'll mark it because it is again visited, right? So what we will do, our c is here, right? So left node will be placed here. We'll now find the rightmost, okay. We'll take out the left node first, okay, and then we'll find the rightmost, okay. And we will check first. We'll check if left node is not equal to null. If left node is not equal to null, then find rightmost, okay. So here left node is not equal to null, right? So find rightmost. Rightmost is this only, make connection. connection is not established, make connection. So I made a connection, okay, and after making connection, what I'll do, I'll shift this. So here a mark that it is visited first, and now as I'm shifting it to the left, always shift C to the left, okay, always shift to C to its left, because we always make the left call first, right? In the recursion also we always make the left call first, and if left call is not succeed, then we go to right call after printing, okay. So we will handle the right calls or the calls to the right by ourselves, okay. So now C will come here, okay, C is coming here, okay. So now left node is now null. So when the left node is null, we know that this left side is ended, this left side is ended. So that means that this person is also included in my in order. So 5 will be added in my in order, okay. Now 5 will be added in my in order, and now I'll go to the right, okay, because left thing is exhausted, right? Left calls are exhausted, so I'll go to the right, and already a right connection is already been made. So I'll go to this again, I'll go to this again, this C. So this is with the third time, and C will come here, okay. C will come here again, place left node to this, okay. We placed left node to this. So this time I have seen that the rightmost node left, what we do, we check if left node is null or not. If it is not null, find the rightmost is the 5 only, right? Rightmost is the 5 only, then calculate the right of rightmost. So right of rightmost is pointing towards the C only. So when it is pointing towards the C, then this means that my child, that means this child can point to its parent, that means it can access its parent, but it is not possible, right? It cannot be possible in a tree. So what happened here, I made a connection by myself, okay. I made a connection by myself. So what I need to do, I need to add it, okay. I need to end this connection because I don't want to change my tree, okay. I'll end this connection, and this C will come this side now, will come to its right now, okay, will come to its right now. So when it come to its right, then it will again make a left node. So left node will null this time, okay, it is null this time. So when it will be null, what it will do, it will say that okay, it is the last person which should be added. So 11 will be added now. Okay, 11 will be added now. Now what I'll do is I'll shift this C, I'll shift this C to its right. So 11 is added and left calls are exhausted, so shifted to the right. So C will come here, right? C will come here, and now the connection is not ended. This is visited 2 times, okay. Is it visited 3 times or not? I actually forgot to write, but no problem, we'll see again. The left node will be placed here this time. Now we'll find okay, one more thing, why am I writing this cross? Because I want to show you that how many times in this traversal we are visiting a node, a single node, how many times we are visiting, okay. I want to show you that. So if you will do it by yourself, then do it in the same way, okay, so that you can also see that how many times you are visiting a node. So C will come here, right? C will come here, and then this time ln will be placed here. Give me the rightmost. So it will say this is the rightmost. So right of rightmost. So right of rightmost is not null. It should be null. If it is the right of rightmost, then it should be null. But this time it is saying that right of rightmost is pointing to our current. That means it is pointing to its parent. It is not possible. So that means I made a connection. I have already processed this tree. When we see that a connection is already made, okay, when we visit a point where the connection is already made, then that point will be considered as the point where the left tree is being processed, okay. Here the left tree is being processed. So when the left tree is being processed, what I need to do, I need to end this connection, right? I need to end this connection, and then I'll add this 2 to my collection of in order, okay, to my collection of in order. And then after that, what I'll do is I'll take this to the right, because the left tree is already been completed. So in the 2 cases we move to right. We move to right in 2 cases. Sorry. So in right, 2 cases are first is if left call is exhausted, okay, or there is nothing in the left call, exhausted. Okay, or second thing is if left tree is processed, left tree is processed, that means completed. If left tree is processed or there is no left call, then we come to right side. Okay, so we'll add to our collection, okay, of in order, and then we will take this C to its right. So here we have C. Okay, so it is visited 3 times and it is visited 4 times, and it will ln will go here to find the leftmost, right? So it is visited 3 times, and then again it will come here. So it is visited the first time right now. Okay, when it is visited first time, we'll place the left node is null. Okay, so when it is null, then it means that it will be the part of my collection of in order, so it will come here. Okay, and now after this, what I'll do, add it and make it right call. So go to its right. So I'm saying call, but I'm not using recursion. I'm showing you that how I'm going to do this, how I'm going to do this. I'll make some connections. Okay, and how I'm making this connection, you will see that in code. Okay, so this time this 5 will go to this, right? And then what will happen, the C will move to this. This is how 5 will move to 9, because the C will move. Okay, C will move, we'll place the left node here, we'll take out the rightmost. The rightmost of right is null. If it is null, make a connection. I made a connection. After making the connection, shift it to the left, so it is visited once, and then C will come here, so it is also visited twice. Okay, so now what will happen is, see, the left node is null this time. I'll make a left node, but that is null. So when it is null, then it is the part of my collection. So add this to my in order. So I added this to my in order, and now 9. Okay, what I'll do now is I'll shift it to the right, because left calls are completed, so shift it to the right. So right is this 9, right call is this, so right will take it to 9 again. So it will again go to 9, twice it is visited, then C will come here. So again left node will come here, and it is visited thrice. Okay, so it is visited thrice, and what will happen? So now left node is here, it is not null, so give me the rightmost. So rightmost is saying that right of rightmost is not null, it is pointing to current. So it is pointing to current, that means it is pointing to its parent, but it cannot point it to its parent in a binary tree. That is not possible. So I made this connection. That means I process that tree. I have already processed that tree. So when I have already processed that tree, then what I'll do, I'll add 9 in this. Okay, I'll add 9 in this. I'll end this connection from here. Okay, and then what will happen is, after ending this connection, I'll move to its right. So when it will move to its right, then its right is already null. So now it will point to null, current will be null. So when current will be null, we need to stop at that point. Okay, so this will be the in order. Is it same? Yes, it is. See, 2, 7, and then 5, then 6. 2, 7, 5, 6, then 11, then 2, then 11, then 2, and then 5, then 4, then 9. Okay, it is the same in order, but I haven't used recursion. How I haven't used recursion? See, let us see that in our code. Okay, I hope that this is completely clear. If it is not clear, then I request you to kindly go back and see this dry run, and if possible, you can do that by your own, because you can get the clarity by doing this dry run by your own. Okay, and the later part which is remaining, if some dots are remaining, then I'll cover those dots in this code. Okay, in this code. So let us go to the code now. Okay, so this is our code. So let us do the code. So we are going to write this code first of all in C++. So this is it. So this is the function that we need to complete. So how we can complete it? Is we have this Morris traversal function in which we need to return a vector. Okay, we need to return a vector of this in order tree. Okay, we need to traverse in order. Okay, and we need to return this vector. So yeah, so let us make a tree here. Okay, first of all, what we used to do, current here, left node here, right? So make a current. So first of all, make a current node. So as I need to return answer in vector, right? So I'll make an answer vector. So vector of int answer, okay. And then after that, what I'll do, I'll make a tree node that is equals to tree node current, right? And that will point towards head first, I mean root, okay, root. So tree node current is equals to root, and then after that, what we need to do, we need to place a we need to do some work. So till when we need to do some work, till it is not equals to null ptr, okay. At this, till this point, we need to do some work. So after this, what we need to do, we need to make a left node, right? So tree node left node is equals to left of current, right? Current left, right? This is what our left node is. And then we were checking if our left node is equals to null or not. Left node is equals to null ptr, or it is not. Why we are checking that? See, it can possible that my c is here, right? It is possible that my c is here because I'm first my c was there, then I take it here, then I take it here. So at this time, if I make my left node, then it is pointing to null. So when it is pointing to null, then it is showing that my left call are being exhausted, then my left call are being completed, right? Left calls are being completed, so that means I need to add this person to my in order, because I have traversed my left side completely. So when I have traversed my left side completely, so this person would be added in my in order, and then this side, right side, will be processed, right? So what I'll do, I have seen that if my left node is null, so at that time, what I'll do is, I'll say that in this answer, push back my, what we need to push back, we need to push back this current val, right? So push back this, and then go to its right, go to its right. So that means current is equals to current right, okay. Current is equals to current of right. So this is what it will do here, okay. At the point where left node is equals to null pointer, then at that time we need to add this point, because we have already completed our left calls, okay. We'll add it, and then we'll go to right side, okay. So we have already seen this in our dry run, so let us not discuss more about this. And then second condition is when our tree is like this, and this is our node, this is our current node thing, and this is our ln. So what we need to find the rightmost of this left node, right? Rightmost of this left node, make a connection, okay. And when to make a connection? When there is no connection. This is the point where we need to remember. When there is no connection, make a connection. When there is a connection, destroy the connection, okay. So what I will do, I will find the rightmost, okay. I'll find the rightmost, that means tree node rightmost node is equals to, I'll write a function for it, get rightmost node, and I'll pass a left node, and I'll pass my current. So okay, left node, because I need to find my left my rightmost of this rightmost of this left node. But why current? See, I have already told you that if my left node is this, and the connection is already been established, okay, and the connection is already been made, but at this time also I need to see that this is my rightmost node which is pointing to the current. this is only my rightmost node which is pointing to current this time. Okay, rightmost node on is not this, as we can see that this is pointing from its right, but this time also this is only the right. Okay, because this is what I have made, this connection is what I have made. In the actual tree it is not the rightmost. Okay, so this is what I'm trying to say, that this is why we need to send this current. Okay, I hope that you got the point that why we are sending this current at this function. Okay, so what we'll do, we'll check. What we'll check? We'll check if the rightmost node, if the right of rightmost node is equals to null. Okay, if it is equals to null, then that means at this point I need to make connection. I need to make connection because the connection is not made here. Connection, CONNECTION. Okay, connection. Make connections, or we can say threads, or we can say thread. Else we need to, this means that if we are reaching this at this block, then this means that the connection has already been made. Okay, the connection is are already available there. Okay, there is only two cases possible, that is the rightmost node will have a connection or it will not have a connection. Okay, so if it will have a connection, then what I need to do, I need to destroy those connections, or threads, and add that to your destroy those connections or thread, and add that current value to your answer, right? Because that will also be our point where we have seen that my left subtree is already been processed. Okay, destroy those connections or thread and add that to your current val, add that current val to your answer. Okay, so this is what we will do. Okay, so let us do that. So now I have seen that, I'll show you with the help of this tree so that you can get this point easily. Okay, so this is how our tree was. So what we will do is see, my ln is here, my current node is here, right? So I'll find the rightmost. This time there is no connection, I'll make a connection, not to this. How I can undo this? Okay, not to this but to this, right? I'll make a connection. So let us make it. So now I have seen the right of rightmost is equals to null pointer. So in that point, what I'll do is rightmost node right is equals to current. Okay, and what else I need to do? I need to shift that current to over this point, right? After this we used to do change the position of this to this, right? We shift this to this. Okay, and then we make again here, we'll find again the leftmost of it, rightmost of it, again make a connection, again shift it to this, again place this, again make a correct connection, right? So this is what we used to do. So this is what we are doing here, and let us see. Okay, so what we are going to do, rightmost of this rightmost node of right is equals to current, and the second thing is again see, ln was here. Okay, so after making the connection, what I'll do is I'll shift this. That means current That means is equals to current, and current is equals to current of left, right? So this is what it will do. Okay, and then after this, what I'll do is the rightmost node of right is null pointer at that time, and this time it is not equal to null pointer. So that means the connection is already been established. So when I already have a connection, then what I will do at that point, I need to erase that connection and add that number at that current value to my C. It was like this. So I was saying that when my this point, when my right of left node, that means this was the rightmost node, right? The rightmost node is this. So the right is already been connected. So it is already connected. So at this point, what I need to do, I need to change this connection. So I need to destroy this connection. So how I'll do this, I will rightmost node right. Okay, the right of this rightmost node is equals to null. Okay, I'll point it towards the null. Okay, it as it was before. So after this, answer dot pushback, what do you need to push back? You need to push back this current val, right? So this is what you need to push back and shift it to the right. Current is equals to, okay, because left call are already been completed, so shift it to the right. So the same thing you did here. Okay, this you did here, and this is completed. From here, return your answer. Okay, there could be some typing error. Okay, there could be some typing error, but it is almost done. And the last thing that is remaining is that is tree node. The function was get rightmost node, right? Get rightmost node. It is not that hard. What you need to pass is just a tree node where you need to give it left node, and second is a tree node where you will pass current. Okay, these are the two things. So what you will do is, you will see while my left node, it was left node, right? Yeah, left node, yeah, it was left node. So my left node dot right. Okay, left node is here, I need to find the right. Okay, so left node right is not equals to null. Okay, if it is not equals to null, then it is some valid point. Okay, and left node right is not equals to at current also. Okay, because if it is pointing to current, then at that time also it is the leftmost node. Okay, it is the rightmost node also at that time. If it is pointing to the current, then also I'll say that it was the rightmost node. Okay, it was the rightmost node. So my rightmost node will be what it would be, I'll at this point, if it is not equals to this or this, then at this point left node is equals to left node right. Okay, left node of right, and then simply return left node. Okay, so this is what we will do. I hope that this is completed. So what I will do is, I'll now give it a run. So okay, yeah, so let us go and give it a run. Check it this side. Run it. Okay, some compilation error, no issues. We'll see what are these compilations error. So in line 20, we have seen something is out of scope. Line 20, left node pointing to the right. Okay, it is not null, it is null PTR. So it is Done. Yeah, anywhere else I have written null. So give it a give it a run. Okay, it is accepted. Let us give it a final submit for all the test cases. So this is it. Okay, so I hope that you got this question completely. Okay, it was quite an interesting question, quite an easy question that we did by using, without using any recursion, just with the help of a simple loop. Okay, and with the help of some logic, with the some help of some logic that we have built. Okay, it is called Morris traversal. Okay, it is called Morris traversal. And one more thing I need to discuss, that is these stars. What are these stars? These stars were the time complexity, the number of times it was visiting each and every node. Okay, so if you will see, all the nodes are almost visiting thrice, right? Almost visiting like some are visiting 4 times, some are visiting 2, some are visiting, some all are also visiting 1 time. So the minimum number of time I am visiting a node is at least once. Okay, at least once I'm visiting all the nodes. And second thing is the average which I'm making here is 3, right? So I can say that my complexity is precise complexity is 3n. If I'll talk in terms of O big O, then it is on. Okay, then it is on. But if we will talk precisely, then it is visiting every node 3 times. Okay, average, in an average it is visiting every node 3 times. So we can say 3n is the time complexity. Okay, so I hope you got this point also, and this code. Okay, this is the code where we have put a left current pointer. Okay, find its left node. Okay, and after this is the current pointer, this is the left node. And after checking it, we checked that if the left node is null or not. If it is null, we did some work. If it is not null, we did some work. Okay, so I hope that you got this question completely. And after this, we'll meet in the next question. The next question is pre-order traversal. Okay, with the help of Morris traversal. So till then, goodbye, take care, and don't forget to like the video and subscribe the channel. Goodbye, take care.